Hello everyone, I hope you all are keeping well. In our last video, we have studied about population density of chapter 13, organisms and population. In this video, we'll be studying about the topic growth models. So, now the question is how this population growth takes place, how this growth actually happens. Now, when we start looking at the exact pattern of growth using graph, we get to see that there exist different types of growth models. Growth can also happen in a number of ways. It is not necessary that the growth has to happen in a linear way. So, there are different ways growth can happen. So, let us look at the growth models. The first one is the exponential growth model. Now, when the growth happens, when there are more births and there is more immigration, and more immigration when the weather conditions are more favorable, when unlimited resources are available for survival. Similarly, more births can happen when all the conditions are suitable, enough resources are there. So, basically, whenever the resources are adequate, the resources are present in sufficient amount. In other words, you can say when the resources are present in unlimited amount. In that case, the growth will happen very fast. The growth will occur exponentially. So, that is exponential growth model. In this case, growth happens exponentially because of enough resources. It is like if you have so much food to eat, what will happen? Your weight will increase. So the same thing happens here. When the large number of resources are available everywhere, so the organisms will utilize the resources and the population will keep on increasing. So the population will grow exponentially. So this is the graphical representation of exponential growth. Okay, if you see this graph, which is the J-shaped graph, if you see this graph, which is the J-shaped graph, it is the graph of exponential growth, okay, which is plotted against the population density, which is denoted as N, against the time. That means when the time passes, the population density increases at a very faster rate. Okay, so with time, the population density will increase exponentially. How do we express exponential growth mathematically? We know that population increases very fast. So that means we are bothered about population density, which is denoted as N. Population density is denoted as N. So, as per our knowledge in exponential growth, the value of N will increase very fast. So, let us say that at time t, at any time t is equal to 0, means the initial time is 0, the population density or the value of population density is denoted as N0 or N0. And at time t is equal to t, that is after time t, the population density is denoted as Nt. This is how we denote population density at different times. Now, as per us, this increase from N0 to Nt would have been very huge because the population is growing exponentially. What would be dN by dt? What would be dN by dt? This is a question. That is what we are interested in. That is how fast the population is growing. So whenever we define exponential growth, we say that dN by dt is equal to b minus d into n, where B is the birth rate, D is the death rate. Since here the population is increasing very fast, that means number of births are more than number of deaths. So we can say that B is greater than D. So B minus D, that is the net increase in the number of individuals, into N. Okay, B minus D, birth rate is more than death rate. B is greater than D. So B minus D into N, right? Where N is population density. Why are we considering N? Because we are talking about per capita birth rate or death rate. You remember, whenever we are talking about B or D, we are talking about per capita birth rate or death rate. That is the number of births or number of deaths that happens per organisms per year. So per year has been taken care by dt. Per year has been taken care by dt, and per organism has been taken care by n. So dn by dt is equal to B minus D into N is the equation which defines the exponential growth of a population, and the curve represents, in the last slide you have seen this graph where this type of curve you have found, that is J-shaped curve, growth curve you have found. Okay, so the equation dn by dt is equal to B minus D into N defines the exponential growth of the population, and the curve represents the same relationship, that is dn by dt is equal to B minus D into N. Now if this B minus D is denoted as R, small r, where R is known as the intrinsic rate, where R is known as the intrinsic rate of population increase. So B minus D actually decides how fast the population grows or how fast the population density would increase with time, because dn by dt will be more. That means the population is growing very, very fast. So this is how the exponential growth is denoted exponentially. So here dn by dt is increase or decrease. dn by dt is increase or decrease in population in unit time period. So let us see how do we get this exponential relationship. So for that we'll just try to derive the exponential growth equation from this very equation. Okay, the equation which we have is dn by dt is equal to r into n. Okay, now you can write this as dn upon n is equal to r into dt. This can be written like this. Now if we take integration on both these sides, then it is written like this. Integration from 0 to t of dn by n is equal to integration from 0 to t of r dt. Okay, now if you have, these are the basic mathematical equations. Okay, integration, if you want to simplify, okay, say for example integration of 1 by x into dx is equal to logarithm or log x. Okay, so if you want to write integration of dn by n, it is written as log n. Okay, and integration of dx is equal to x. So integration of a dx is written as a integration of dx is equal to a x, right? So like this, the integration of r dt is equal to r integration dt is equal, that is equal to rt. Okay, so what will you write here? This equation can be written like this. It is equal to log n with the limit 0 to t is equal to rt. How rt? That has been explained here. Okay, so this can be written as log n0 nt, sorry, so let us continue with that. It is I will write from here log n with the limit 0 to t is equal to rt. This can be written as log nt minus log n0, that is equal to rt. Okay, now this can be written as log n t upon n0 is equal to rt. Okay, now again this can be explained mathematically. Further explanation is, say for example, log of a raised to x is equal to y. This can be simplified. This can be written as x is equal to a raised to y. How? See, kick this a. If you kick this a, it will go here, right? So it is written as x is equal to a raised to y. This is the way to remember. Okay, so log of e raised to x is equal to, say for example, rt. It will be written as x is equal to e raised to rt. Similarly here it is log nt upon n0, okay, to the base e. It is written, it is equal to rt. So if you kick this e, it will go this side. So it can be written as nt upon n0 is equal to e raised to rt. Okay, so further simplification is nt upon n0 is equal to e raised to rt. Okay, where e is the base of the logarithm, right? Further you can write nt is equal to n0 into e raised to rt. So this is the exponential equation, that is the population density at any time t is equal to population density at the initial time t is equal to 0 into e raised to rt. Understood? So that means as the time increases from 1 to 2, 2 to 3 and 3 to 4, what happens to the net value? So the net value keeps increasing exponentially because e raised to 1, e raised to 2, e raised to 3, and so on. So value increases too much. So the population increases very, very fast. So this is how we derive exponential equation, and that is how it is defined as the exponential growth. But this type of population growth takes place only when the resources are unlimited, because without resources the population would not increase. So looking at the exponential growth equation, what can we interpret? Okay. This is the integral form of exponential growth. We have already studied this. Nt is equal to n0 into e raised to rt, where nt is the population density after time t, n0 is population density at time 0, and r is the intrinsic rate of natural increase, where e is the base of the natural logarithm. Okay, so now if we look at the exponential growth equation, that is dn upon dt is equal to b minus d into into n. There are different cases. Case 1 is if b is greater than d, then b minus d is more than 0, that is, it is positive. Therefore you can say that dn by dt is also positive. So if dn by dt is positive, the population is increasing with time, so the unbounded growth occurs, right? In the second case, where b, that is birth rate, is less than that of death rate, okay, then b minus d is less than 0, that is, it is negative. Therefore you can say dn by dt is also negative. So population is decreasing with time, so it leads to extinction. Say for the example of tigers are becoming extinct nowadays. It is because the birth rate of tigers is less than that of death rate. Okay, death in tigers is occurring more than that of birth, right? And the third case is if b is equal to d, then at that time, if we keep b is equal to d in this equation, then what will happen? dn by dt is equal to 0. So change in population density is 0. So no change in population. So population remains constant, or we can say that this is the scenario of stable population, that is, population is neither increasing nor decreasing in size. So if 10 births are taking place in a year, then there are 10 deaths taking place in a year. So overall population density will remain the same. So these are the three scenarios that can be interpreted by exponential growth equation. I hope this growth model is clear to everyone. Now we'll start with the second type of growth model, and that is logistic growth model. In exponential growth, we have learned that if the resources are unlimited, then the exponential growth happens. But in reality, the resources are not unlimited. The resources are limited. So there are limited resources, but a lot of organisms to survive. So there exists a competition between various organisms for their survival. And as well as we all know, who survives, the fittest survive. So when we talk of limited resources, there can be no exponential growth. So the type of growth happens with limited resources is called logistic growth. So when we talk about logistic growth, it becomes very important to know about carrying capacity. About carrying capacity. This is carrying capacity. Now, what is carrying capacity? What is the meaning of carrying capacity? It means the maximum number of organisms that a habitat can support based on its resources. Okay, once again, the maximum number of organisms that a habitat can support based on its resources is known as carrying capacity. Now, as the resources are limited, the habitat can support the limited number of organisms. So, the maximum number of organisms that can be supported is called the carrying capacity of that habitat. So once the carrying capacity of the habitat is reached, the population cannot grow any further. So when we talk of logistic growth, this is how the growth happens. Okay, you can see here, this is how the growth happens. This is the curve which is formed by the logistic growth. Here, the population increases with time. You can see population is increasing with time. As the time increases, the population also increases. But it reaches a stage beyond which the population doesn't increase. Here you can see, when it reaches to this stage, the population doesn't increase further. And this phase is termed as the carrying capacity. That means the population cannot increase any further. Okay, this is what carrying capacity, where the population cannot increase further. Now there are three phases in logistic growth. The first phase, that means this phase, starting from here to this phase, this is called the lag phase. Then from here to here, it is the log phase. And the third phase, this phase is the stationary phase. Where the population does not increase. So let us see these phases one by one. The first phase is the lag phase. Lag phase denotes slow growth in population. Looking at the graph, you can see, once again, let us see the graph. Looking at the graph, you can see that as time increases, the population also increases. See, here the time increases, population also increases, but slowly. So, the logistic growth can be denoted as dN by dt is equal to Rn into K minus N upon K, okay, where K is the carrying capacity. Based on this equation, we get the sigmoid curve. Based on this equation, the curve which is obtained is the sigmoid curve. Right? This curve which you can see, okay, this is the sigmoid curve, whereas the curve which is obtained in the exponential growth is the J-shaped curve. Okay, this for logistic it is sigmoid curve. So here K minus N denotes how many organisms may be added to a population at a given stage. An entire K minus N upon K. This is entire fraction. Okay, so the entire fraction K minus N upon K denotes the fraction of carrying capacity that is available for further growth. So that's the mathematical expression of logistic growth. Looking at the expression, let's see what happens during the lag phase. During the lag phase, the value of N is very small. Okay, value of N is small because N is on the y-axis. N, when you have seen the graph, you have seen that N, which is population density, is on the y-axis. Okay, since N is small, as the N is small, the dN by dt is also small. However, it will increase but slowly. Okay, as it is small, there will be increase, but the slow growth will be there. Therefore, it is the phase of slow growth because dN by dt is increasing slowly. Okay. Now, if we talk of the second phase, which is the log phase, in this phase, the increase is very fast because as the time passes, the N increases. Okay, so N increases. As the N increases, dN by dt also increases. That means growth is rapid in both, that is in the lag phase and in the log phase. N is less than K. Okay, in both these cases, N is less than K. And therefore, there is the scope of increase in population. Now, if we talk of the third phase, that is stationary phase, at this phase, N is equal to K. Okay, population density is equal to the carrying capacity. Now, since carrying capacity is reached, the population growth rate decreases. Population doesn't increase any further. So, if you put N is equal to K in the equation, that is dN by dt is equal to R into N into K minus N upon K. If you put N is equal to K in this equation, then right hand side will be 0. Okay, N is equal to K. So if you keep here, if you replace N by K, then what you will get? The right hand side will be 0. So dN by dt is equal to 0, which tells us a constant population. Okay, so interpretation of logistic growth equation we have already done. Lag phase, where N in lag phase, N is less than K. N is very small, therefore dN by dt is small. So slow growth takes place. Slow growth. If we talk of log phase, where again N is less than K, in both the cases I have already written here. N is less than K, N increases, therefore dN by dt also increases. So rapid growth. And in stationary phase, N is equal to K, therefore dN by dt is equal to 0. So constant population. Okay, so this is all about the logistic growth. In this video, we have studied about the growth models, that is exponential growth model and the logistic growth model. In our next video, we'll be studying about population interaction.